Okay, in this video, we're going to talk about events being independent. Okay, so two events, we'll say A and B, are independent. Well, by definition, we're going to define it as if the probability of A given B is just the probability of A, and the probability of B given A is just the probability of B. So what that really means is that the probabilities of A and B respectively are not affected by the other. Right? So, in other words, the probability of A given B is still just the probability of A. Given B doesn't change it at all. Okay? Now, if you remember our definition of the probability of A given B, or B given A, this one is the probability of A intersect B over the probability of B, right? And so if we rewrite that, probability of B times the probability of A given B, we get the intersection, right? But if we have independence, then this right here is just the probability of A, right? So the probability of B times the probability of A is the probability of the intersection. And that's really useful when we have independence. So when we have independence, this is really a bright marker, we can find the probability of the intersection just by multiplying each of the probabilities together. That's very nice. Now, remember a while back when we talked about mutually exclusive, and I said to you, two events are mutually exclusive if they cannot happen simultaneously. That is, if A and B are disjoint. Okay? That is, A intersect B is the empty set. That is, probability of A intersect B is 0. Now, mutually exclusive is not independent, and people often confuse those. Ooh, that's bright. Don't confuse these. Independence means they don't affect each other. Mutually exclusive means they do, right? If A occurs, B can't. If B occurs, A can't. So independence and mutually exclusive are not the same thing. Okay? Okay, let's do a quick problem with independence, just an example, and then maybe we'll have time to do a proof in this video. Okay, so here, let me just set up the problem. This is from your book. A parallel system functions whenever at least one of its components work. Consider a parallel system of n components. Suppose that each component works independently with probability 1/2. Find the conditional probability that component 1 works, given that the system is functioning. So, I'm not very good at drawing, but we have this circuit, and we can either go this way, this way, this way, or any of the n different ways, okay? And if we go down this way, right, so we can think of it like a switch, right, which is either open or closed. If it's closed, then the circuit can travel through. Let me try to draw another one here. So we have another open circuit, then it's open. I'm trying to draw my pictures back. Oops. So maybe this one has an open circuit. Well, my drawing is not great. But if they're closed, so you can imagine, if one is closed, so let's make that closed, well, then the circuit gets through, right? So we only need one of them to be closed in order for the whole system to work, okay? All right, so if we named each one of these events, so I could say A sub 1 is the event component 1 works. Okay, and A sub 2 component 2 works, and so forth. So really we have n of these events, component n works. Now, this thing works if at least one of them works, right? So this is, so the probability of, well, so the system would work really if I said A1 union, A2 union, A sub n, right? And so if I wanted to find the probability it works, I really just need to find the probability of this union. And we know a way to do that, right, with inclusion exclusion. However, that's a lot of work, okay, because something else we know is that this thing fails, and sometimes that's easier, right, to find the complement than the direct one. It fails if none of them work, right? So that is if A1 doesn't work and A2 doesn't work and so on, AN doesn't work, right? Now this is where we get to use independence. So the probability this thing fails is the probability of this great intersection. And we saw up here that it works or it fails with probability 1/2. We get to just split this up into 1/2 times 1/2 and so on, 1/2 or 1/2 to the n. Okay? So we know it. So if I wanted to find the probability that the system works, it would be 1 minus 1/2 to the n. Okay, however, that wasn't quite the question. The question was find the conditional probability that component 1 works given that the system is functioning or working. All right, so really, based on the way we've named our events, we're looking for the probability that A1 happens given the system is working. Okay, now we just use our definition of conditional probability. So this is A1 and it works over the probability that it works. Now, A1 and it works really is just the probability of A1, right? Because that's a subset. A1 intersect W is just a subset of A, right? If A1 works, then the system works. So this really becomes the probability of A1 over the probability of W. So we did all the work over here, and we get 1/2, because A1 works with probability 1/2 over 1 minus 1/2 to the n. Okay? Okay. That's just one example of using or applying or having the benefit of independence within a problem. We will see a lot of that in Chapter 4 when we start looking at named discrete distributions. But another thing that I want you to be able to do is to do some proofs using some of our set theory and probability rules. So here's something that's true. If A and B first of all, what does it mean to show two events are in identity that we like, which if you want to look at it in terms of a picture, just to remind yourself, A and B is this part, A and not B is that part. So we just split it up into the sum of, or we look at A as the union of disjoint sets, and so we can take their probability just by adding them. Okay, so now we get to use the fact that A and B are independent. We need to show something to do with this guy, right? But we don't have that yet. So we're going to take the probability of A is equal to, now we can split this up using independence, the probability of A times the probability of B. We can't do anything with this yet, so don't split it up or you're assuming the conclusion, right? All right, we're going to move this guy on over here. We get the probability of A minus the probability of A times the probability of B equals the probability of AB complement. Ooh, I think we could factor probability of A times 1 minus the probability of B equals the probability of AB complement. Ooh, what's that? Probability of A times the probability of B complement. And that's equal to the probability of AB complement. So we were able to show this based on that. So other ones that you might be asked to show and that you might want to think about is, given that A and B are independent, show A complement and B complement are independent. But I will leave that one for you.